All right, we're going to practice some more hypervalency. Let's take a look. Remember, you're going to use the electronegativity differences to determine which element gets to follow the octet rule and which one is hypervalent. So you're going to try to draw the phosphoric acid molecule, H3PO4. You're going to try to make sure that all the elements that need to follow the octet rule are, but figure out who might end up being hypervalent. A couple of rules of thumb that you're going to follow. Look for the atom with the most possible bonds and place it in the center of the molecule. We learned that rule before. Who can make the most possible bonds? But in this case, when you're thinking about the most possible bonds, you also want to think about, what if it's hypervalent? Will that change the number of bonds that it can make? Also, you're going to attach the lowest electronegative atoms to the highest electronegative atoms. So that's another rule. For instance, oxygens don't want to be bonded to each other because they're both really high in electronegativity. They're going to go after things that have lower electronegativity. Pause the video, see if you can draw the H3PO4 molecule. Okay, so now that you've had a chance to do that, let's see what you got. This is the H3PO4 molecule, phosphoric acid. So phosphorus has 5 valence electrons. You've got a lone pair and 3 unpaired electrons. So you might think phosphorus is only going to make 3 bonds. But because oxygen is so electronegative, an oxygen can come in and break up the lone pair of that phosphorus and turn 3 bonds into 5. What you'll notice on here is that the 4 oxygens are all attaching to the phosphorus because they're all going for something with a lower electronegativity. In addition, the hydrogens are also attaching to the oxygens because hydrogen has a lower electronegativity than oxygen. Okay, let's try another. Pause the video and see if you can draw the SF4, sulfur tetrafluoride molecule. Okay, so you're probably realizing now fluorine has a higher electronegativity than sulfur, so all 4 fluorines are going to attach to the sulfur. So you're going to get something like this, where basically the 4 fluorines attach to the sulfur. Sulfur normally would make 2 bonds, but one of its lone pairs is going to have 2 more fluorines attached to it, so one of its lone pairs is broken up, the fluorines attached to those 2 electrons, 1 lone pair remains intact. So, some important rules for hypervalency. You can split lone pairs, but if you split them, both electrons must be used for chemical bonding. So every time you split a lone pair, you're making 2 more chemical bonds. You may not have any single unbonded electrons left over. So again, if you break up a lone pair, both must be used. If you do get the rare situation of a single unbonded electron left, we call that a free radical. Free radicals are not common because they are so highly reactive. As soon as a free radical is created, that atom is going to immediately look for an extra electron somehow, some way, whether it be grabbing it from the environment, attaching to another element. It is going to pair up that electron. So free radicals are very short-lived and highly reactive. Sometimes you hear about on TV commercials for shampoos or foods, it's like, this will get rid of the free radicals. And that free radicals are damaging, and one of the reasons is that they are highly reactive. All right, so I'd like you to try now to draw the SF5 molecule. Pause the video. See if you can draw it. All right, well, one thing you may notice is that you can't do it, can you? Because SF5 is what we call a free radical. Notice that if we were to break up the lone pairs of sulfur, we could have the 2 normal unpaired electrons that would make 2 bonds. We break up a lone pair here to make SF4. When we try to add the 5th, we've got this unpaired electron left over. So you cannot make the SF5 molecule without it being a free radical. However, remember that there is never just one of anything. In the real world, you've got millions and millions of these atoms all interacting with each other. So if two SF5 free radicals were to meet, those two unpaired electrons could then form a bonding pair and bond the two sulfurs together. So these two SF5 molecules meet each other, and next thing you know, you've got S2F10. That looks something like this. All 6 valence electrons are being used in the bonding of this molecule. Okay, we're going to have one more video on following hypervalency and see if you guys can do some more practice problems.